Welcome to Curiosity Explain. The depths to the stars. Curiosity has no limits.
The universe is full of strange mysteries. Scientists have long been fascinated by black holes, regions in space where gravity pulls so much that even light cannot get out. They form when the center of a massive star collapses in upon itself, creating a singularity, a point of infinite density. The boundary around a black hole is known as the event horizon, beyond which nothing can escape the gravitational pull. Our solar system, a familiar neighborhood of planets, asteroids, and comets. But what if there's more to the story? What if there's a hidden giant lurking in the distant reaches? The Kuiper Belt, a region beyond Neptune filled with icy bodies. For years, astronomers have studied these objects, noting their peculiar orbits. We noticed that several Kuiper Belt objects shared similar orbital characteristics. They were clustered in a way that seemed unlikely to occur by chance. Dr. Anya Sharma explained, the orbits seemed to point to something larger influencing them. The leading hypothesis? Planet 9, a hypothetical planet with a mass several times that of Earth, orbiting far beyond Neptune. Its gravity could explain the strange orbits. But finding Planet 9 is no easy task. Its immense distance means it's incredibly faint and difficult to spot. We use powerful telescopes, like the Subaru telescope in Hawaii, to scan the sky for faint objects moving at the expected rate of Planet 9, Dr. Kenji Tanaka explained with technical detail. He is an astronomer involved in the search. Astronomers also employ sophisticated algorithms to analyze vast amounts of data, filtering out background noise and identifying potential candidates. The search continues, pushing the limits of our technology and knowledge. Every observation, every calculation brings us closer to either confirming or refuting the existence of Planet 9. Whether Planet 9 exists or not, the quest to find it is revolutionizing our understanding of the outer solar system, revealing new insights into its formation and evolution. In the vast expanse of space, there exist cosmic enigmas that defy our everyday understanding. These are black holes, regions where gravity is so intense that nothing, not even light, can escape. Let's begin with the basics. A black hole is formed from the remnants of a massive star that has collapsed under its own gravity. But what happens around these celestial vacuum cleaners? One key feature is the accretion disk. This is a swirling mass of gas and dust that orbits the black hole, gradually spiraling inward. As the material accelerates, it heats up to millions of degrees, emitting intense radiation. The accretion disk is a cosmic beacon, a lighthouse revealing the presence of an otherwise invisible giant, Dr. Eris Thorne said, scholarly. Dr. Eris Thorne, astrophysicist, explains the significance. Now let's address a rather gruesome phenomenon, spaghettification. Imagine an object falling into a black hole. The gravity on the side closer to the black hole is much stronger than on the far side. This difference stretches the object, elongating it into a thin, noodle-like shape. But black holes aren't just cosmic destroyers. They also emit something called Hawking radiation, a theoretical phenomenon where black holes slowly lose mass over vast periods of time. Hawking radiation suggests that black holes aren't eternal. They evaporate, albeit over timescales far longer than the age of the universe, Professor Lena Hansen explained with scholarly insight. Among the most famous black holes is Sagittarius A, located at the center of our Milky Way galaxy. Another well-known black hole is M87, residing in the galaxy Messier 87. In 2019, it became the first black hole to be directly imaged, a monumental achievement in astrophysics. Dr. Eris Thorne said, with a scholarly tone, that image confirmed decades of theoretical work. It showed us undeniably that these objects exist and behave as Einstein predicted. Dr. Thorne emphasized the breakthrough. The Event Horizon Telescope, a global network of telescopes, made this possible. By combining data from multiple locations, they created a virtual telescope the size of the Earth. Black holes continue to fascinate and challenge scientists. They hold clues to the fundamental laws of physics and the evolution of the universe. The study of black holes is not just about understanding these exotic objects, Professor Lena Hansen explained with scholarly insight. It's about pushing the boundaries of human knowledge and exploring the very fabric of space-time. Professor Hansen concluded with a broader perspective. Imagine the universe as a vast ocean filled with galaxies like shimmering islands. But what if I told you that what we see is only a fraction of what's really there? Welcome to the enigma of dark matter. For decades, we've been observing things that simply don't add up according to our understanding of gravity and visible matter, Professor Eleanor Vance explained. That's Professor Vance, an astrophysicist specializing in dark matter. She's here to help us unravel this cosmic mystery. One of the biggest clues comes from galaxy rotation curves. These curves plot the speed of stars as they orbit the center of a galaxy. According to Newtonian physics, stars further from the galactic center should orbit slower, Professor Vance explained, analytically. He clarified that this unexpected behavior implies that there is more mass than we can account for through visible stars and gas. This unseen mass, exerting its gravitational pull, is what we call dark matter. Another piece of evidence comes from gravitational lensing. Massive objects warp the fabric of space-time. When light passes by these objects, its path is bent, much like a lens focuses light, Professor Vance explained, instructively. She explains that by analyzing how light from distant galaxies is distorted, scientists can map the distribution of mass, including dark matter. These observations consistently point to the existence of dark matter, a mysterious substance that makes up about 85% of the matter in the universe. Despite knowing it's there, we still don't know what dark matter is made of, Professor Vance explained candidly. Scientists are exploring various candidates, from weakly interacting massive particles, or WIMPs, to axions. Experiments are underway around the world, searching for these elusive particles using incredibly sensitive detectors. Unlocking the secrets of dark matter will revolutionize our understanding of the universe, from the formation of galaxies to the ultimate fate of the cosmos, Professor Vance said passionately. So the next time you look up at the night sky, remember that there's much more than meets the eye. The universe is full of mysteries, and dark matter is one of the most profound. For decades, dark matter has been the invisible elephant in the room of cosmology. We know it's there because of its gravitational effects on galaxies and galaxy clusters, but we can't see it, touch it, or directly interact with it. The quest to detect dark matter has led scientists down numerous paths, each fraught with challenges and intense debate. The leading candidate for dark matter is the WIMP, or Weakly Interacting Massive Particle. These particles are theorized to interact with normal matter through the weak nuclear force and gravity, explained Dr. Eris Thorne with a scientific tone. Dr. Eris Thorne, a leading astrophysicist, explains the WIMP hypothesis. One of the primary methods for detecting WIMPs involves building massive underground detectors, shielded from cosmic rays, in the hopes of catching a WIMP as it collides with an atomic nucleus. Dr. Lena Hansen explained cautiously that they had seen some tantalizing hints of potential WIMP signals over the years. But so far, none of these detections had been definitively confirmed. She added that the signal-to-noise ratio was extremely challenging. Dr. Lena Hansen, an experimental physicist, discussed the challenges. Dr. Ben Carter explained that the lack of definitive WIMP detections has led some to explore alternative dark matter candidates, such as axions. Dr. Ben Carter, a theoretical physicist, introduces the axion. Axions are hypothetical particles that are much lighter than WIMPs and interact very weakly with matter. They were originally proposed to solve a problem in particle physics, but they also happen to be a viable dark matter candidate. Dr. Ben Carter explained scientifically that axion detection relies on different techniques. He mentioned that one prominent method involves using strong magnetic fields to convert axions into detectable photons. Experiments like ADMX are at the forefront of the axion search, using resonant cavities and powerful magnets to amplify the faint signals produced by axion photon conversion. There's a lively debate in the dark matter community about which candidate is most promising. Some argue that WIMPs are still the best bet, while others are increasingly focused on axions and other alternatives, Dr. Lena Hansen explained, with a balanced tone. Dr. Hansen highlights the ongoing scientific debate. It's crucial to explore all viable possibilities. Dark matter could even consist of a mixture of different particles, Dr. Eris Thorne said, optimistic. Dr. Thorne emphasizes the importance of exploring all options. The search for dark matter extends beyond WIMPs and axions. Other proposed candidates include sterile neutrinos, dark photons, and even primordial black holes. Each candidate has its own set of theoretical motivations and experimental challenges. The diverse approaches are essential to increasing our chances of discovery, Dr. Ben Carter explained encouragingly. Dr. Carter underscores the importance of a diversified search strategy. Beyond direct detection, scientists are also pursuing indirect detection methods, searching for the products of dark matter annihilation or decay in space. Gamma-ray telescopes, like Fermi-LAT, are scanning the sky for potential dark matter signals, but distinguishing these signals from astrophysical backgrounds is a significant hurdle, Dr. Lena Hansen explained realistically. Dr. Hansen discusses the indirect detection challenges. The scientific debates surrounding dark matter are not just about particle candidates. They also extend to the fundamental assumptions about the nature of gravity and the distribution of dark matter in galaxies. Dr. Eris Thorne explained that some researchers are exploring modified Newtonian dynamics, or MOND, as an alternative to dark matter. He said that MOND proposes that gravity behaves differently at very low accelerations, which could explain the observed rotation curves of galaxies without the need for dark matter. However, MOND faces challenges in explaining the behavior of galaxy clusters and the cosmic microwave background. The search for dark matter is a global effort, with scientists from around the world collaborating on experiments and sharing data, Dr. Ben Carter said, emphasizing the importance of international cooperation in making progress in this challenging field. Dr. Carter emphasizes the importance of international collaboration. The quest to detect dark matter is one of the most ambitious scientific endeavors of our time. Despite the challenges and debates, the pursuit of this elusive substance continues to drive innovation and deepen our understanding of the universe. For years, the mystery of Planet 9 has captivated astronomers and space enthusiasts alike. The evidence suggests something massive lurks in the outer solar system. But what if it's not a planet at all? Today, we delve into the fascinating hypotheses and alternative explanations for the Planet 9 enigma. The initial evidence, the peculiar orbits of several Kuiper Belt objects, strongly hints at a gravitational perturber far beyond Pluto, Dr. Eris Thorne, an astrophysicist, explained with scientific clarity. Dr. Thorne is an astrophysicist who has been researching Planet 9 for over a decade. He believes in the Planet 9 hypothesis, though recognizes that many alternative theories exist. But what if the clustering of these objects isn't due to a single massive planet? One alternative suggests it's a collective effect. Dr. Lena Hansen, a cosmologist, explains scientifically, imagine a collection of smaller icy bodies, much larger than typical Kuiper Belt objects, but still significantly smaller than a planet like Neptune. Their combined gravity could create the observed orbital patterns. Another intriguing possibility involves a primordial black hole. These are hypothetical black holes formed in the early universe. If one happened to be captured by our solar system, its immense gravity could explain the Planet 9 effect without any light emission, Dr. Kenji Tanaka, theoretical physicist, explained with scientific precision. Perhaps our understanding of gravity itself is incomplete on such vast scales. Modified Newtonian dynamics, or MOND, offers a radical alternative. Professor Evelyn Reed, a theoretical astrophysicist, explains scientifically, MOND suggests that gravity behaves differently at extremely low accelerations, like those experienced by objects in the distant solar system. This could mimic the gravitational effects attributed to Planet 9. New data is constantly refining our understanding of the outer solar system. The Vera C. Rubin Observatory, when fully operational, will provide unprecedented observational power, potentially confirming or refuting Planet 9's existence, Dr. Eris Thorne said with hope in their voice. So, is Planet 9 a real planet, a collection of smaller objects, a primordial black hole, or a sign of modified gravity? The answer remains elusive. The search continues, driven by our insatiable curiosity about the cosmos. Want to delve deeper into the alternative explanations for Planet 9? Click the link in the description to read the full article and explore the science behind this cosmic mystery.